So let's start. In the statement, check the spin matrix equation 4.145 and 4.147 obey the fundamental commutation relation per angular momentum equation 4.134. So equation 4.145 and 4.147, we have to show that this equation follow the commutation relation for angular momentum, that is equation 4.134 or not. I have to write the equation 4.145 and equation 4.147. So equation 4.145 and 4.147 are Sx is equal to h bar divided by 2 and 0 1 and 1 0. This is for Sx. For Sy we already know that this is the equation 4.147 and 4.145. You have to check that after this video. So we have to show that this follow the commutation relation for the angular momentum or not, that is equation 4.134. so that is Sx and Sy is equal to iota h bar is z. So now our required result is that Sx and Sy is equal to iota h bar is z. So we have to show this, that this is equal to iota h bar is z or not. So we have to show that. So I am putting the values of Sx and Sy in this equation, and after that we have an equation that is Sx and Sy is equal to Sx Sy minus Sy Sx. This is, let's suppose I number this number one equation. So I am putting values of Sx and Sy in this equation. So the values are Sx value are given, so I am putting simply that values in this equation. So h bar divided by 2, 0 1 and 1 0 are the Sx value, and Sy values are 0 minus iota and iota 0 h bar divided by 2. Now Sy is equal to h bar divided by 2, 0 minus iota and iota 0, and Sx are same, 0 1 1 0 0 1 1 0 and h bar over 2. So h bar over 2 and h bar over 2, if we multiply this, so we get h bar square over 4, and similarly minus h bar square over 4. So h bar square over 4, if I take this common, so we left with 0 1 1 0 and 0 minus iota and iota 0 minus 0 minus iota 0 minus iota and iota 0 and 0 1 1 0. We take common h bar square over 4. So now if we multiply this first row with the first column and then first row with the second column, matrix multiplication, you better know this, first row with the first column and after that first row with the second column, and after that second row, this is the second row with the first column and second row with the second column. So we have to multiply this, and I get the result from the multiplication that h square this is the result is h bar square over 4. From this we get h bar square over 4, and if we multiply this, so I get iota 0 and 0 minus iota. This is iota 0 and 0 minus iota. You have to multiply this, minus iota 0 and 0 iota. We get this, and now I just simply subtract this, so I get h bar square over 4, and the remaining are 2 iota and minus will be plus, so iota plus iota will be 2 iota, and 0 minus 0 is 0, and 0 minus 0 is again 0, and minus iota, here is minus iota, and this sign minus will be multiplied to this, so minus iota and minus iota, we get minus 2 iota. Now I have to take common minus 2 iota or simply 2 iota, so I left with h bar square over 4, and here 2 iota is common, so I left with the 1 0 and 0 minus 1 here, so 2 will be cancelled with 4, so now h bar square over 2 and iota here 1 0 and 0 minus 1. So I can write this like iota h bar over 2, and h bar here, h bar into h bar is h bar square, so I can write like this 1 0 0 minus 1. So here h bar over 2 1 0 and 0 minus 1. If you look at the equation 4.147 and 4.145, so the SZ value, I mentioned that h bar over 2 1 0 and 0 minus 1. So I can simply put equation 4.145 in this equation, so I h bar, and here we get SZ, so here SZ. So the final equation that I get is Sx and Sy is equal to iota h bar Sz. This is the first part of the numerical. Now the second part of the numerical is show that the Pauli spin matrices equation 4.148 satisfied the product rule. Here is the product rule, and we have to show that the Pauli spin matrices obey this rule, satisfied this rule or not, and here is the cyclic and its reverse order, so we have to show this now in the second part. So the second part is part B. Here we go, the second part is part B. Here is the second part. Okay, so I have to write the Pauli spin matrices that are sigma x. This is not s. Instead of s, now we can write sigma x is equal to 0 1 0 1 1 0, and similarly sigma y is equal to 1 0 minus iota and iota 0, and sigma z is 0 1 0 1 0 and 0 minus 1. This is the Pauli spin matrices equation 4.148. So now we have to prove that this satisfied the product rule or not. So Sx and Sy, I have to take product of the Sx with the sigma x, and sigma z with sigma z, and sigma y with sigma y. So what are the results? So let's check it. sigma x with sigma x. So the value of sigma x is 0, 1, 1, 0, and again 0, 1 and 1, 0. Here is the values. So if we multiply the matrix multiplication, so we get 1 is sigma x and sigma x multiplied with sigma x, we get the result 1. Now similarly the sigma y and sigma y, here is sigma y and sigma y, if we multiply this, so similarly our answer is 1, and sigma z with sigma z, so we get the answer is 1. So from all three multiplication, sigma x, sigma y and sigma z, we get only one answer. So I can write this in general form. From all three we get one answer. So here is the general form of this equation that I can write like that: sigma j and sigma j is equal to 1. Now how can we write sigma j and sigma j is equal to 1? So j can be x, it can be y, and it can be z. So the values of x, y, and so we can put the value instead of j, x, y, and z. Here is the values. So now I have to multiply this again with the sigma x with sigma y, and similarly sigma y with sigma z, and sigma z with sigma x. So here is the multiplication: sigma x with sigma y. First I multiply sigma x with sigma y. So what we get from this: sigma x is 0, 1 and 1, 0, and sigma y is 0, minus iota and iota 0. Here sigma x and sigma y. So from this we can get from the multiplication, if we multiply this with the first row with the first column, so 0 multiplied by 0 is 0, and 0 multiplied by iota is 0. Similarly plus 0 multiplied by minus iota is 0, and 1 multiplied by this 0 is 0. So we get 0 here. It can be multiplied with the second row, it can be multiplied with the first column and second column. So we can get, you can multiply this, here we can get 1 and 0 and 0 and 1. You can multiply this, and this is iota and this is minus iota. If we multiply this first row with the first column, then first row with the second column, and second row with the first column, and second row with the second column, so we get iota, 0 and 0 minus iota. So the answer, if I take common iota, so we get 1, 0 and 0 minus 1 here. So here's the answer of sigma x and sigma y if we multiply this. So now we know that iota 1, 0 and 0 minus 1 is equal to the sigma z. We already write this, that sigma z is equal to 1, 0 and 0 minus 1. So I can simply put here, instead of 1, 0 and 0 minus 1, sigma z. So sigma x and sigma y will be equal to iota, still remain the same, and here I can put the sigma z from the 4.148 equation. So I can get this answer. Now if I multiply the sigma y with the sigma z, here sigma y, and if I multiply this with the sigma z in the cyclic order, so I can get iota sigma x, and similarly sigma z with the sigma x. So the answer is iota sigma y. So it is the cyclic order from the vector triple product. If I, this is the let's suppose this is some circle, and here I put the suffixes I and j, and let's suppose this is k, and this is in x, y and z. So according to the suffix rules, if we change the places of the suffixes, so the sign will be changed to the negative. Matlab we means we replace this, reverse this. And if we change the order, so the order doesn't matter, the sign will remain the same. Like here is the rule, if I, j, k are the suffixes and its summation, so the negative sign will be appear in the summation if I change the places I, k and j. Here I change the places of the suffixes, not the order. I, j, k and I, k, j. I, j, k. So I change these places I, k, j. I can write this is I, j, k is equal to the summation of the I can write this like k, I and j. I, j, k, and I can write k, I, j. So now the order are changed. If we change the order, so the sign is not changing, but if we change the places of the suffixes, so we get a negative sign. So here we get, so here is the positive answers. And now if I change or reverse the direction of the given suffixes, so I can paste a negative sign here. So here is, I can replace this, I can reverse this, so sigma y and sigma x. Now here is sigma x and sigma y, and I can write here sigma y and sigma x. Now the places of the suffixes are changed, so we can put the value of sigma y is 0, minus iota and iota 0. Here is the value of sigma y, and sigma x is equal to 0, 1 and 1, 0. If we multiply this, so I get a value iota minus 1 and 0, 0, 1. Here we go. So now the answer to this is minus iota, and sigma is sigma z. This is the value of sigma z. Minus here is the only negative sign. If I take common this, so minus iota and 1, 0 and 0 minus 1 will be here, and there this is the value of sigma z. So I can put here sigma z. So sigma y and sigma x is equal to minus time sigma z. And now similarly, if I reverse the direction for the all sigma y and sigma x, y, z, so it means if we change the places, so we can paste a negative sign in the cyclic order like that. And if we change only the order, so the equation is same, like we get 1 here, plus 1. If we change the order only, so here is if this is 1, 2, 3, 1, 2 and 3, so I, j, k, I can get 1, 2 and 3, and I, j, k, similarly j, k and I, so 2, 3 and 1, 2, 3 and 1. So now k, I, j, so 3, 1 and 2. Here is 3, 1 and 2. And if I change the places, so not the order, only the places are changed, so I can get the values. Now minus 1 here, I will get minus 1 if the order are changed. So here is I, j, k, and now k, j, I are the values, or k, I, j are the values here. So k, j, I, so we get 1, 3, 2 here, and similarly 2 3 1 here, 2 1 3 here, and 3 2 1 here. So the if we change the order, so totally the cyclic order can be reversed and we can get a negative sign only, and the total result are still the same.